So gravitational field strength, really it's acceleration, so that's a vector quantity. So gravity is the attraction of masses, so the gravitational field lines are directed inward to the mass, just like we drew. Also from our G equals big G times m2 over r squared, we can see that gravitational field is inversely related to distance from the mass producing. So we would say our G is inversely proportional to r squared. So if I'm thinking about, like, this is my M2, or my object producing that gravitational field, and I draw my arrows pointing in, if my object that I'm comparing it to, or that it's pulling on, is, say, right here, so this is like, say, point A, and then let's draw another one like farther out, and we'll say that's point B. Which one is going to have a greater field strength exerted on it, do you think? Why? Because it's closer. Okay, so yeah, A would have a greater field strength because it's closer, because it's more exposed to that force. Okay, so A will have exposed to stronger G fields because closer. And point B will be exposed to weaker G fields because far away. So if an object leaves basically our atmosphere of Earth, it will still have gravitational strength from the Earth pulling on it, but it's going to be less. Okay? Once an object will leave a certain part of our atmosphere, it's exposed to so little of Earth's gravitational field that it won't be pulled in as strong. So let's think about this graphically then. So let's write on this side, this is our gravitational field strength, so this is our G, and here is our distance in M. Put the units here. So it can either be newtons per kilogram or meters per second squared, either one. So it will have a graph similar to y is equal to 1 over x squared. So the graph will look as so. So we can see that it actually never reaches 0. So it's always still somewhat exposed to that gravitational field, even though it's very far away. So it will be so small that it's almost negligible, but it still exists.